In example 2.5, power function n to the d is a constant, but it is a positive constant, not necessarily integer. But when we prove it, first we consider the simplest case. N is a positive integer. That's simplest. Under that assumption, we can apply L'Hopital's rule, infinity over infinity, in determinate form, many times. Yeah. All right, d times, actually, d times. Then our result, the limit is 0. After we complete this case, this case, we need to go to the general. So we need to remove the integer assumption. So this time, we assume d may not be an integer. So d is not an integer. D is not an integer. Okay? So if we still apply L'Hopital's rule, we may have a problem, where to stop, right? Yeah. So we may have some problem. Yeah. Yeah. There is a possibility you can still do it. Yeah. Still do it because, actually L'Hopital's rule, in this case, if you still want to do it, then, because this exponent number will never be 0. But it could be negative, right? It could be negative. When it is negative, your power function is at a denominator. Yeah, you can still prove it. Yeah. Right? Yeah. So if you apply L'Hopital's rule, under the assumption, d is not integer, so then you can use this way. Yeah, but there is another way we can do. So we use although d is not an integer, but the ceiling function of d is an integer, right? Yeah. Ceiling function of d is an integer. Okay? Yeah, it is an integer. Yeah. And we know it is greater than d, right? The ceiling function of d is strictly greater than d. It's an integer, okay? Yeah. So then we use the ceiling function of d as a stepstone to help us to find the limit. So here, let me just quickly show you the step. All right. This time, x to the d over a to the x. Can we split it into two parts? Yeah. The first part, x to the d over x to the d ceiling function. How about that? Yeah. All right? Yeah. The second part, x to the d ceiling function over a to the x. Okay? Yeah. When we use, we insert x to the d ceiling, as a, bridge, stepstone. And we proved this limit is 0, right? And this one, actually this limit also 0, right? Because denominator grows faster than the numerator. Denominator, you can get a x to the ceiling of D minus D, right? Yeah. And this is the infinity. Yeah. So 0 times 0, you get 0. So here you can see when we go to the general case, we can use the integer case to help us to get what we want. Yeah. Yeah. So that's here I want to use this example to show you in problem solving. This is the method commonly used in our problem solving. So why we always start from the simplest cases? Because the simplest cases could be used after we prove it. We can use the simplest cases as our starting point for other cases. Here, we just, find appropriate bridge to reach other cases. So that's this example 2.5. All right. Next, let's complete the last two examples. 2.6. Yeah. Log base 2 of n belongs to bigger of root of n. Root of n. Yeah. Yeah. And for this case, still L'Hopital's rule, continuous version, take derivative, pretty straightforward. All right. Because it's infinity over infinity. Okay? Yeah. So then we take derivative, numerator, denominator, we apply the formula, then do simplification. After the simplification, you can see it is not indeterminate form. Because the numerator is a constant, denominator goes to infinity. Then the whole fraction goes to 0. Yeah. So then we can, from continuous variable, then we can move to the discrete variable. So we have the conclusion. Yeah. All right. Then the last example, 2.7. This time, slightly different. This time we want to do a little more general. So natural log bigger of n to the d power function, and we only require d is a positive number. Yeah. It's true. All right. Yeah. All right. Now we still apply the L'Hopital's rule on the continuous variable version. All right. There. So after the first round derivative, infinity over infinity indeterminate form. So we apply L'Hopital's rule the first round. Numerator 1 over x, denominator by the power rule of derivative. After simplification, we have limit of 1 over d times x to the d. So this time it's not indeterminate form. So this time we can take the limit directly, because the numerator goes to infinity. Yeah. So the result, final limit, equals 0. Yeah. Then we can go back to the continuous. Yes. So here, go from the continuous variable back to the discrete variable. So we have the conclusion. Yeah. So after these examples, I want to make the, final round comments about the summary. Yeah. So after today's class, I will post a homework assignment. Yeah. And here, there are two important examples here, closely related to our homework assignments. Yeah. Here, I want to talk about these two examples, two results you can use in our homework assignment. All right, yeah. The first result I want to talk about is from example 2.5, this one. Okay, yeah. So we now, after we proved it, we can use it as the result. Yeah. And here you can see what we need, the condition, D, any positive number, and A, any positive number greater than 1. That's the only requirement, right? Yeah. Yeah. So this is a general result. But when we apply this general result on concrete numbers, then your understanding, your specific feeling could be different. Yeah. All right, so here, for example, yeah, D, arbitrary positive numbers, right? Yeah, arbitrary, here I just use the positive integers, D. Yeah. But D must be fixed. After you choose a positive integer D, you have to fix it. Yeah. Your N is variable, you can change, but D, as soon as you choose it, you cannot change it. Okay, you fix it. All right, so here, how I like to take D equals 1 million. How about that? That's a large integer, right? Yeah. Now, if D is 1 million, then our power function becomes n to the 1 millionth. N to the 1 millionth. Think about how large is this function. Okay? We know the power function. Growing very fast. N to the 1 millionth. Very fast. Okay? All right. All right. Then I will ask you to compare order of growth, how fast this function grows, comparing with another function. This function is 1 point, yeah, because A must be greater than 1, right? Yeah, but I just make it a little more than 1. 1.0, many zeros, then 1. Very close to 1. Yeah, very close to 1, right? Then I raise to nth power. Yeah, nth, exponent number n. Okay? Yeah. These two functions. Now, if I ask you which one grows faster, can you get an idea? Yeah. These two functions. The first one, base is n to the 1 millionth. It's a power function, large power function. The second one, exponential function, but the base very close to 1. 1 point, so many zeros. Yeah. Then 1. Then this number will raise to nth power. Can you get an idea, which one, when n is very large? Yeah? Because we mainly consider extremely large n numbers. For small n numbers, we don't worry. Okay? So we want to see when n becomes an extremely large number, integer, which one grows faster? These two functions. Yeah? Think about that. Yeah. Because many of you, when you answer this question, yeah, you use your intuition, right? Yeah, intuition. But sometimes your intuition may not be correct. Yeah, that could happen. Yeah. Because your intuition comes from your experience. Yeah. So your experience, sometimes may not, because these two numbers extremely large. You do not have a chance to experience so large numbers, right? Yeah. How can you produce these two huge numbers? Yeah. Extremely hard. Yeah. So if you cannot produce these large numbers, very far in the universe, yeah, you couldn't see the end. You cannot get a visual understanding. So how do you apply your intuition? Yeah. So that's the main problem. Okay? Yeah. But here, based on our result, which one is larger, right? Based on the result, you can pick the larger one. So in our homework questions, you will see similar questions like this. So we need to connect to our results, because it could be different from your intuition. This is one example, the first example. The second example, it comes from 2.7. Yeah, 2.7. The second example. We know natural log of n belongs to big O of n to the d, but at this time we only require d is a positive number. Okay? Yeah. Any positive number, we have this result. Yeah. All right. So now I ask you to compare these two functions. The first one is natural log. We know when n goes to infinity, natural log function also goes to infinity, right? Yeah. That's the first one. And the second function is a power function. Yeah. Power function with positive exponent number. Yeah. And we can use any exponent number, any positive exponent number. We have this result, right? Yeah. So here, I want to choose one special positive number, but that one is very small, 0.00, yeah, many zeros, 1. Okay? Yeah. That is a qualified power function, right? Yeah. So this small exponent number satisfies the condition d greater than 0. 0. Greater than 0. Okay. Yeah. But yeah. So you need to, take root, right? Yeah. So this one, if we write the root form, yeah. So maybe 1 million. That number, okay? 1 millionth root of n. Yeah, we know the larger the root number, then the whole function becomes smaller, right? Yeah. 1 millionth root. Okay? How small it is. Yeah. Now we want to compare it with natural log function and which one grows faster. Yeah. Okay? So you need to answer this question. So if you apply your intuition, yeah, so you may feel differently, right? Yeah. Based on intuition. Yeah. 1 millionth root. You may feel that's not very large, right? After you take 1 millionth root, may not be that large. Okay? Yeah. So how do you get an idea which function eventually will be larger? Right? Yeah? Yeah. So we have result here. Okay? So these two results. Yeah. So sometimes you may not feel quite matching your own understanding, yeah, your own imagination. Yeah. But we know our intuition sometimes may not be correct. Yeah, may not be correct. Yeah, so you need to be very careful. Yeah. All right. Yeah. Oh, just a minute. Let me set timer. I forgot to set timer. Yeah. So at this point, we finish module 2. Yeah. Finish module 2. Yeah. So now let's move to module 3. Another very important module. But our homework assignment will cover first 2 modules, module 1 and 2. Yeah. All right, let me switch to module 3. Recursive algorithm, module 3. (8.1) First view of recursive algorithm. Yeah. So this topic, very important, very useful. Yeah. So let's understand recursive thinking. Why we need to study this special way of thinking. Yeah. All right. Yeah. We are used to straightforward thinking. Yeah. People, if you do not get a training in this recursive thinking, then most people like to use the non-recursive thinking, right? Yeah, yeah, because they feel more comfortable using non-recursive thinking. Yeah. All right. Yeah. Yeah. But yeah, and many problems can be solved in both ways, non-recursive way and a recursive way. Many problems. And we want to compare these 2 different ways to solve the computing problems. Yeah. All right. And the answer of the first question. Yeah. First, we want to answer this question. The answer of this, our current question, is because the recursive algorithm is very powerful. We want to use the power of recursion to solve computing problems. Very, very important, very powerful. That means for some of the relatively hard computing problems, if you do not use a recursive algorithm, that could be extremely hard. Most people cannot do it. Most people cannot solve some of the relatively hard computing problems without using recursion. Couldn't make it. So, but if you apply the recursive thinking, recursive algorithms, you can quickly solve it. So that's the power of recursion. That's the reason we want to learn and use it in our problem solving. All right, but later, so for this part of A, I want to convey this idea. Let you see it. Let you feel about it. The importance and why it is so useful in problem solving. All right. Yeah. All right. Now let's do comparison. The first one, non-recursive, so we call it iterative. Yeah. You need to solve it without using recursion, then you need to use iterations, right? Yeah. For loop, while loop, iterations. Yeah. So that's the way if we do not use recursion. Yeah. The second way, recursive way. We want to compare these two methods, their advantages and disadvantages. Yeah. Quickly do that comparison. Advantages for iterative algorithms, comparing it with the recursive, it's less. In general, it uses less resource. That's an advantage. Yeah? The advantage part is the less resource. Okay? Yeah, but the implementation part is harder. That's the disadvantage. Okay? So one advantage, one disadvantage. Consumes less computing resource, but for relatively the hard problems, when you write a code, could be very hard. All right, so that's the. But for recursion, disadvantage, resource-wise, you need to use more resource. What? More resource. Okay, computing resource. I will explain this. What do you mean resource? What's the resource? Memory, storage, memory, computer, memory resource. Yeah. All right. For the easier implementation. All right. So here, let me explain why recursive algorithm, you need to use more resource. Yeah. You need to pay more. That means, so when you, so, you need to pay the cost. Nothing is free, right? Yeah. In order to get this powerful tool, you need to pay more in computing resource, more. Yeah. Why is that? Oh, sorry. Yeah. Why is that? Yeah. Let me use a simple diagram to explain. All right. Yeah. Yeah. So currently, all our high-level programming languages support recursion. Yeah. So that's a great thing. Early computer programming languages did not support recursion. Very early. Yeah. Yeah. So that the question is, we need to understand inside the one typical high-level programming language, how to implement recursion. Yeah. So right? Yeah. So you call, you do recursive function call. Yeah. It can be implemented. There is some internal support, right? Yeah. So the internal support, yeah, it uses a special data structure. Yeah. So this special data structure, you can use it to implement recursion. So what's that special data structure? Stack. Stack data structure. You learn, right? Yeah. In your data structure course, you learn it. It's a very simple data structure. Okay? Yeah. This data structure has some property called first in, last out, right? Yeah. So people call it first in, last out. Okay? First you push it into the stack, the last one you retrieve it. Okay? Or sometimes the last in, first out. Yeah. You push into the stack. Yeah. So here, yeah. So the stack like this. You push in. Okay. The first one you push in is at the bottom, right? So the last one you get it out. Okay. The last one you push in on top, right? So then the first one you retrieve it from the stack. So the stack has this property. Right. Now we can use this stack property to implement recursion. Okay, all right. Now, let me show you a simple example. Okay, all right. Suppose we need to calculate a recursive function f of n. Based on the recursion, how it works, when we calculate f of n, we need to use f of n minus 1 value. Yeah. But in order to calculate f of n minus value, you need to use its previous value, f of n minus 2, and so on, right? All the way to, let's say, f of 1, okay? You need to do recursive function call like that, right? Yeah, to implement it in a stack. Yeah. First, yeah, because your goal, you want to calculate f of n. It's not available. How do you handle it? It's not available. So you push it into the stack. So f of n, the first number, you push it into the stack. Yeah. Waiting inside the stack, right? Then, yeah, but you need to use the value of f of n minus 1. But if it's not available, so you can only push it into the stack f of n minus 1, and so on. Then f of n minus 2, and so on. Okay, all the way up. All right. Yeah. Last one you push in f of 1. Okay. All right. Then, yeah, because f of 1, for recursion, we need to have the base case, right? Yeah. The base case, f of 1. F of 1, yeah. Let's say, because we already pushed it into f of 1. Yeah. That means f of 1 is unknown, right? Yeah. In order to calculate f of 1, we need to use f of 0, and we assume f of 0 is the base case. Base case. Base case, it is known. Okay? Yeah. So we apply the base case, we can calculate f of 1. So f of 1 is known. Pop it out. Yeah. F of 1 is pop it out. And do the calculation. Yeah. F of 1 relies on f of 0. So we can find the value of f of 1. So f of 1 is known. Yeah. Yeah. Then the next one to be popped out, f of 2. Pop out f of 2. F of 2 rely on f of 1. F of 1 value is known. So we can use f of 1 to get f of 2. Then f of 3 and all the way down to the bottom. That's the way we use this stack data structure to implement recursion. Okay? Yeah. Okay. Any recursion can be implemented in this way. Not too hard, not too hard. Okay. Can you see how much resource we need to use in this way? This whole stack, that's the computing resource. Okay? Yeah. This computing resource in the main memory. And we know our main memory is quite limited, right? The size, the amount of main memory, quite limited. Not hard drive, it's main memory. Okay? RAM, yeah, it's quite limited. Okay? Yeah. 4G, 8G, 32G, right? 64G, yeah. That main memory, not hard drive. Your hard drive is much larger, right? 1T, yeah, that large. Because your main memory is much more expensive than hard drive. Yeah. So 32G, that's pretty good, right? Yeah, 3264. That's really good, okay? All right. But that's limited, quite limited. Okay. And when you use more memory resource, your RAM resource, we know all the programs running on your computer all need to use the memory resource, right? They share the memory resource. If one of the programs uses too much memory resource, then all the other programs will slow down, right? Yeah. All the programs using the same memory, share the same memory resource, slow down significantly. No. That's the drawback of this recursion. No. Use quite a lot computing memory resource. Yeah. All right. Then there is another potential problem. Yeah. Based on this limitation, so you can see there is another potential problem you need to be aware of. When you write a program, recursive function call, yeah, that's very common. When you do problem solving, you need to apply recursion frequently. Yeah. So there is a potential problem you need to be aware of. That is, yeah. Think about if when you do recursion, you push into the stack and make your stack very deep. That could happen, right? Yeah, because your data size is very large. Yeah? You push, large number of unknown numbers, function calls into your stack. You grow your stack. So there is a problem because the stack grows too fast and you run out of your memory resource. When that happens, you will get a stack overflow. Stack overflow problem. Yeah. Because the depth of your stack grows too fast, too deep. Okay? Run out of memory resource. In that situation, you get a runtime error. It's a runtime error. The memory cannot do anything. Okay? Yeah. The memory, the runtime error. So you see the stack overflow, runtime error on your screen. Then your program crash. So you know, that's the typical problem, stack overflow problem. Okay, yeah. So when you do the recursion, you need to be aware of this potential problem. Yeah. Although you enjoy the power of recursion, but this problem you need to try to avoid it. Okay, yeah. In this situation, you need to think about a special way to reduce the depth of the stack. Is it possible you do not, grow your stack too fast, too deep, make your stack too deep? Can you, try to use some temporary intermediate computation result to reduce the depth of the stack? Think about it. Yeah. Some solution to reduce the depth of the stack. Yeah, all right. So that's the, some important background information. Yeah. Yeah. All right. Yeah. Next, let's calculate our first example of using the recursion. Yeah. Calculate the factorial. Yeah. Given non-negative integer n, we need to calculate n factorial. Although for this one, we do not need to use recursion, but here we like to use it as the simple example to help us understand recursion, how it works. Yeah. All right. Method 1, iterative method. Yeah. So we just use a for loop. We can calculate factorial easily, right? So that's the first. Yeah. Yeah. Based on the definition of factorial, yeah. So we just do the product. Okay. Okay. Yeah. But here, when we define factorial function here, because sometimes we may need to consider the factorial of 0. So here we define the factorial of 0 equals 1, not a 0. Factorial of 0 is 1, not 0. Can you understand it? Why it is 1, not 0? Yeah. Yeah. It is related to 0, but how do you get a 1? We know 0 is nothing, right? How do you, when you manipulate something like nothing, you get a 1? Doesn't make sense, right? Yeah. Yeah, we will try to understand this. Yeah. 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 It may not be quite that intuitive, yeah, but later when we get more information, we will see it makes sense. Yeah. It's correct. Yeah. We should understand in this way. Yeah. All right. Yeah, so let's get more understanding, implementation of this one. Yeah, yeah. For the iterative method, we just use a for loop. We can find the answer easily. Yeah. But here we want to use the second method, recursive method, to help us, get some good understanding of recursive algorithm idea. Yeah. Here we use the general problem solving approach. So this is a very general problem solving. Recursion. Yeah. We understand from the general problem solving view. Yeah. All right. Divide and conquer. Yeah. So divide and conquer. We connect it to divide and conquer approach. Yeah. We know this general approach, divide and conquer, is very useful in problem solving. Okay? Yeah. Here we need to use it a little bit, but it is the topic of our Module 4. Our Module 4, we will learn a lot of divide and conquer applications. Yeah. All right. First, remember, we learned the principle before. The problem is easier when the size is smaller. General principle, right? Yeah. That's the general principle. When the size is smaller, yeah, the problem tends to be easier. Yeah. So we will use this principle in recursion. So we want to, by applying divide and conquer, we want to make our problem sizes smaller. That's the general consideration. By divide and conquer, the original problem, the size is too large. So let's divide it into several subproblems. So each subproblem, the problem size smaller, so we can conquer it relatively easier. So here we take this approach. When you work on problem of the current size, subproblem one by one, the current size, assume that a problem of a smaller size has been solved. Smaller problem size has been solved. So you can use its result, right? Yeah. So the reason you assume it has been solved because you can use its result. Yeah. So then you have the recursion. Okay, all right. So then, step 3, fix the gap through a recurrence relation. How do you connect a known solution of a smaller problem size with the unknown solution of the current problem size? You need to make connection, right? Yeah. So there is a gap between them. Yeah. There is a gap between them. Okay? Yeah. So you need to do some work. Actually, this part is the most important part in recursion. Okay? All right. Yeah. 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 For example, this is original problem. Okay? Yeah. The size is like this. Original problem. Right? So then you divide it into smaller problem. Okay? All right. Sub 1, sub 2, for example. Subproblems. Smaller problems, by recursion, you can solve it. You conquer it. How do you conquer it? By recursion. Because you can further divide those two subproblems, right? Yeah. So you can assume there is a way you conquer it by recursion. All right. But that means you can find a solution of sub 1 and a solution of sub 2. But how do you combine these two solutions, right? You need to do some work to combine. Okay? Yeah. So you need to do some combine work. Do some combined work to connect to, to get a solution of the current problem. Yeah. All right. And that combining part, the extra working part, yeah. And you need to find a formula to connect them. A formula to connect the previous known solutions with the current unknown solutions through this formula, through this recurrence relation. Okay? Yeah. If you can do that, then you can solve the whole problem by recursion. Right? Yeah, it's pretty abstract. Yeah. But later we will study several concrete examples. So you will get better understanding. Yeah. Here we just do some general high-level discussion. Yeah. All right. Next, yeah. Then we can work on this computing problem, factorial problem. Method 2, this time we do divide and conquer. Divide, yeah. Many different ways you can divide it. Yeah. All right, so let us use some symbol f of n to represent factorial function. Yeah. Because when we give a name, capital F, that's the name of the function, then we can call it recursively, right? Yeah. We can do recursion. Yeah. F of n. All right, then we divide it. The way we divide, we chop the last element. Chop off the last element off. Okay? One element reduction. We just reduce the problem size by 1. It's smaller, yeah. It's smaller after the divide step. All right. The problem size is reduced from n to n minus 1. So we get a problem of the smaller problem size, n minus 1. And we assume there is a way that can help us find f of n minus 1 solution. We assume it. We conquer it. We have the solution in the conquer step. All right? Conquer step. How do you conquer? Recur. By recursion. Yeah. All right, so we assume we have this number already. Then the gap. How to make connection? How to fix the gap? There is a gap, right? F of n and f of n minus 1. There is a gap between them. So we need to fix the gap part. How to fix? We use this recursive formula, recurrence relation formula. We connect f of n solution and f of n minus 1 solution. But we need to do some extra work to connect them, right? So this multiplication, f of n minus 1 result times another operand n to that extra work we need to do to get a current solution, f of n. So that's the, typical process of recursion. So we need to get used to this kind of thinking. Okay? Yeah, divide and conquer, making assumption. All right? Yeah, like this. Our data n here, yeah, because n should be positive integer. Otherwise, becomes 0. Right? Yeah. All right. Now, based on this formula, now we want to understand why 0 factorial is 1. Why? It makes sense, right? Yeah. So here, yeah. There are 2 ways of understanding. Yeah, I want to explain 2 ways. The first way from this formula. Okay? Now you agree this formula is correct, right? For the factorial function, it's correct. Now let's rewrite this formula as by doing some simple algebraic operation, right? Divided by n both sides. Simple algebraic operation, f of n minus 1 equals f of n over n. That's legal, right? Yeah. Now, from this formula, let us plug in n equals 1. N equals 1. Okay? Plug in 1 minus 1, 0. F of 0 equals f of 1 over 1. F of 1 factorial is 1, right? 1 over 1 equals 1. Okay? But f of 0, what is the meaning of f of 0? That's 0 factorial, right? F of 0 corresponds to 0 factorial. Here you can see by this formula, our recurrence relation formula, we can derive that f of 0 must be 1 to make sure it works for all the cases. For all the cases, it's compatible. Okay? Yeah. Yeah. So this is our first understanding. So why 0 factorial must be 1? Because consistent. Okay? Otherwise, if 0 factorial is not equal to 1, then when you apply this formula, you may get trouble. Yeah. Inconsistency. Yeah. Right? Contradiction. All right? Yeah. All right. Yeah. So conclusion. Yeah. So you can see through this simple example. Yeah. Yeah. You can see there is this method should be valuable in our problem solving. Yeah. All right. Yeah. Here, yeah, just a few minutes. Yeah. Let me just give you a second way to understand this 0 factorial should be 1. Yeah. This second view, we use our programming experience. Yeah? In our programming experience, we use our typical programming experience to help us understand why this 0 factorial also makes sense. All right. When we do programming, when you take summation, how do you write your code? Summation first. Okay? Yeah. So you need to use a for loop to add up the element in an array. Yeah. So that is, you need to a of 0 plus, you need to calculate a of 1, take summation of all the array elements. Okay? Like that. Yeah. So when you write a for loop, you need to initialize, let's say initialization, your sum variable equal to 0 first, right? Yeah. Then in a for loop, so here, let's assume, certain, so in a for loop, the sum equals sum plus a of I, right? Yeah. That's the way you do the summation in your code.
Does it say for C?
Yeah. So for loop here. Yeah. So here, just some appropriate condition. Okay. So I do not specify it. All right. Then, now let's calculate product. How do you calculate product? All right. Suppose we need to calculate product of sequence of numbers in an array. Right? Yeah. In a for loop. We also use a for loop to calculate this product. Okay. When you do it, temporary variable, similar to that sum, but this time you need to initialize to 1, right? Yeah. Summation you initialize to 0, but for product you need to initialize to 1, right? Yeah. So then, in a for loop, suppose you have for loop, yeah, then you need to update your product variable by times A of I, right? A of I, okay? Yeah. All right. So that's the, our programming experience. Yeah. So we feel very natural, right? Yeah. Think about 0 factorial here. When we work on the 0 factorial, what does that mean? So in this for loop, you have 0 data in this for loop, right? Yeah. Yeah. So you do nothing in this for loop, right? You do not get into the for loop. Yeah. When you hit the for loop, you get out. Okay? When you get out, what is your product, the value of your product? Initial value, right? Yeah? Yeah. Because you didn't do anything in your for loop. That corresponds to 0 factorial. Because your recursive function is not called in this for loop. Okay? In this for loop. Yeah. So you get out, but you get out the current variable you retrieve from this temporary variable. It is 1. It's not a 0. Okay? So that's another way you understand it. Why 0 factorial equals 1. Makes sense. Okay. Yeah, because you're taking consecutive products and the initial value is 1. So if you do not do any work, it's 1. It's not 0. You initialize, when you do 0 initialization, that corresponds to summation. That's not a product operation. Summation, okay? So that's another way. Oh, this way makes sense. Nothing is wrong. All right, yeah, so let's stop right here. Yeah. Next time, we do the second half of part A. Yeah. That's the power of recursion. Next class, power.